Alright, so my name is Robbins, and I'll be doing the group reporting on the bomb calorimeter experiment that we did last week. So start with the goals of the experiment. So really the goals are to become familiar with what the oxygen bomb calorimeter is and what it's used to measure very precisely. Understanding those principles behind it, the thermodynamic principles behind it, and then using those principles to calculate how much energy is released by a certain fuel in the bomb calorimeter. So the background and theory, heat of combustion, or in easier terms would be the energy that's released when you ignite a fuel source. It's the number of heat units liberated by a unit of mass substance when combined with oxygen. So the bomb calorimeter measures that very precisely by putting an unknown sample and igniting it with that oxygen. And upon igniting it, that heat is transferred from inside the bomb to the water bath that the bomb is sitting in. And I'll get to the apparatus in a second, and that'll make a little more sense. But and then when you look at that system, you observe the rise in temperature, and it allows for the calculation of the heat of combustion. So like I said, that main thermodynamic principle is it's pretty common when doing theoretical calculations and conservation of energy or mass of all that. You're conserving energy here. So the heat lost from the bomb equals the heat gained by the system. So the governing equation is your heat energy equals your mass times your CV times your temperature gradient, where Q is the sum of the heat of combustions, mCV is the thermal capacitance, which I will calculate later, and delta T is that temperature gradient. So like I said, that apparatus and procedure right here is the apparatus that is used. So number 6 is your thermocouple, which measures the temperature of the water. 7 is stirring the water. It's just a stir that stirs it so that you get even temperature distribution throughout the whole fluid. And then this right here is your bomb calorimeter, which is basically a steel case with a cap, and you've got two ignition wires that go in and ignite your fuel source. So just again, a brief procedure of how this works, because it would be pretty monotonous to go through the whole thing, but you prepare your crucible right here with your fuel sample, and you put the wire touching it or through it and make sure it does not touch the crucible, because if it touches the crucible, then your heat's going to go into the crucible and you won't ignite your fuel, so that's really important. You need to make sure you seal it very well. Actually, we did not seal it very well. It was really just me, but and then you purge this bomb 3 times. The purpose of that is to make sure that you've got pure oxygen inside the bomb calorimeter, so that it's just keeping a variable constant, basically, so that nothing changes with a different amount. If you're just using air and you purge it once versus twice, you may have some nitrogen still left over or something like that. Once you do that, you pressurize the 30 ATM and then ignite it and begin logging data. So these are my experimental results. This is the known sample versus the unknown sample of miconite. You'll see in the calculations and the overall heat of combustions why your temperature gradient here, how it affects that heat of combustion, and how you have a different temperature gradient for the unknown sample and how it affects that. So these are my calculations. Using that equation that I mentioned earlier, you're going to find, the idea is to find the thermal capacitance of the system. So your system isn't changing, your bomb isn't changing, so if you find that thermal capacitance for the known sample of benzoic acid, then that's going to stay constant when you put a different fuel in, and you can work backwards and calculate the fuel. So that's how I did some of the Q's, where I included the Q of the benzoic acid and the Q of the wire, and that's those 2 values, sum them, and then over the temperature gradient, and this was my thermal capacitance that came out of the system. using that thermal capacitance, like I said, you then just plug it back into the same equation, just rearrange for Q, and this was the heat of combustion that was produced by the micanite. And one thing to note is we try to measure out the weights of the fuel samples as accurately as possible, as close to 1 gram. I assume 1 gram just for the simplicity of the calculations, but they might have varied by 0.1, 0.2 maybe. So when comparing fuel, your benzoic acid has higher fuel or heat of combustion's energy, higher energy released. That's kind of what I expected. I mean, the micanite, if it had high heat of combustion, it would be powering my car, but it doesn't. So, and then gasoline's a lot higher than benzoic acid, so that's probably why it's powering my car instead of benzoic acid. But these are just this is just a graph I found of, your heat of combustion versus, your predicted versus experimental that's been measured, I guess it was for a certain experiment or study that they did. It just kind of shows where different hydrocarbons fall. So finally, some sources of uncertainty. Like I said, that data that I used for this was actually sent to me by Philip. We actually couldn't pressurize the bomb calorimeter high enough, so he sent me that. But when we did do it, I didn't seal, the first time we did it, I didn't seal the bomb on top as well as I should have, and there were bubbles coming out the top, letting oxygen out. Like I said, we couldn't pressurize it up to the top, to the right pressure, and then the way the fuel was assumed, so some of my calculations may be off, but yeah, that's about it. So, any questions?
Any question? Okay, I have just one question. So I'm looking at fuel samples. Like, what do you think determines if a fuel will have high energy content? Like if you take kerosene, petrol, natural gas, like what factor do you think will affect the energy content? Like
density of molecules. Like if you have more molecules in, say, like 1 unit of volume.
Okay, which fuel actually have the highest energy content?
Like from what
Okay, from this, what do you notice?
methane is the highest.
Methane. So, like, why do you think it's highest? Does anybody have?
It's got to do with the formula, huh? Like what methane CH4, right? Or
is that because it easily combusts?
About hydrogen?
Exactly.
okay.
Exactly.
So
the
chemical
more
makeup.
hydrogen content a fuel has, the higher the energy content. And that's why if you look at it, hydrogen actually have the highest energy
Yeah, that's
content.
why pure hydrogen.
Exactly, 142 kilojoule per kilogram or something. So when there's enough hydrogen in a fuel, it actually increases the energy content.
Gotcha.
All right. No other question?